There was one very co-op.
I have to.
So this morning I saw this and I thought it's a funny thing to start with. So this explains why I haven't put out homework 5 yet. Right, so today we'll do something new. So this is optimization. But before that, so just a quick reminder. So homework 5 will be due today, and it'll be actually due on Wednesday, November 20th. Okay. And yeah, so I offset everything a little bit because if we have the Friday things, then you will have a homework due the day after Thanksgiving. So I thought the next 2 homeworks will be due on Wednesday. So all right, so that's how you start. And then so next week I'll be traveling on Tuesday. So you'll have a guest lecture by Suresh on algorithmic fairness. So this will be a fun topic, hopefully, and he gives. I mean, this is a lecture that he always gives, so I can promise you it will be fun. So do show up. Okay. So yeah, and I think it fits well with the theme of the class. Like we always focus on like efficiency, right, and things like this. It's nice to think of other dimensions to algorithm design. Okay. So that's next week, next Tuesday. All right. So until for the last 3 weeks or so, we did randomized algorithms, and we did a bunch of things, and your homework will be on that. And so the plan for the next couple of weeks is that we'll do slightly different topics. So today, this week, we will cover optimization. But very roughly, I mean, it's a course by itself, so I will only be able to do like a couple of lectures worth of stuff. And then we will go on to like hardness of intractability and NP hardness and things like that. Okay, so after the 2 weeks from now. All right, so what is, so let's start looking at optimization formulation. So when you think of optimization, what comes to mind is something like this, right? So you have you have some function and you want to optimize it. So the general problem of optimization is that you want to minimize and maximize some function over some domain. Okay, so the domain in this case is this is the plane, and the z-axis is the value of this complicated function. Okay. And often you want to, and this is a typical scenario in optimization. Okay, so good. So formally, what do we have? So we have a bunch of variables. So let's call them some x1, x2 up to xn, and we have our objective function, which we denote as some f of x1, x2 up to xn. Okay, and these are typically real value variables. Sometimes they can be some discrete value. The interval is some 0, I mean the set 0, 1 or something like that. So we will see examples of both kinds. And you have constraints that basically define this domain. So you have common example could be some 0 less than or equal to some xi less than 1. Sometimes you can have constraints like sum over I xi square equals 1. This is another common constraint that you can consider, and things like this. So this is the abstract optimization set. And before we move on, let's see. So what are the common kinds of things people study about optimization? So people study things like, oh, can you find the optimum value, which is basically can you maximize this or minimize this objective function within this domain? Okay, so that's the kind of problem people study. So it's and there are also other issues like, oh, okay, so sometimes you can optimize this and maybe you get stuck at some local optima, and then there are things like, oh, are all local optima global optima and stuff like this. Okay. Actually, we've seen one such thing, if you remember, for convex optimization a while ago when we were studying local search. Okay. So there are questions like this people try to understand, and there's a huge amount of literature. Some of you may have seen this very thick book by Boyd about Boyd and Vandenberg, the second author, about Vandenberg, I think, second author about optimization. So optimization is a very, very well studied area, and there are all kinds of methods, like mostly like some kind of gradient descent type methods that people use in various settings. And as I was saying, so this is a topic of a full course, so we will not go into the details of optimization. For now, let's think of optimization as a black box that people have developed algorithms for. And our goal will be to use this black box for interesting algorithmic problems. So that's what we're going to see some examples of. Okay? So we want to use this as a black box for some algorithm. Okay, so many of you would have seen optimization in machine learning. Right, so actually, I've asked this before, but how many of you have taken the machine learning course here already, or are taking it now? So all of you have seen optimization in some form or the other. So all of you who have taken this have seen optimization in many forms, I guess. So let me illustrate like two very classic kind of settings. So the first one is it's an example of unconstrained optimization. And this is the regression problem, right? So regression is this very simple question where we have, let me call these observations. So we have such an observation vector. Okay, so we have some v1, v2. These are vectors. That's why I'm writing them out like this. These are some n-dimensional vectors. Up to some Vm, and you would like to find, and let's put them as a matrix, you wish to find, and for each vector you have some corresponding value. Let's call them y1, y2 to yn. These are just some real numbers. This is called the value. It's the value of this observation. And now you want to find some x. Goal is to find some x. This is a vector in Rn such that v times x is approximately equal to 1. So in some sense we want for every I, the inner product of vi with this vector x, this unknown vector x, must be approximately equal to yi. Okay. So it's like saying for every observation you take that observation vector and you take the inner product with this unknown x, you want it to be equal to the value, which is y. That's so this is the most common way of writing out regression, and usually you will not be able to solve this exactly. If this were equality, this would just be a system of equations which you can solve, but often the system will not have a feasible solution. So your goal will be to find some x such that this vx minus y squared is minimal. Okay. So Vx is a vector, right? So Vx will be an m-dimensional vector, and this is an m. Okay. Rm just means m-dimensional real space. Okay. So optimization is one place where I tend to assume common notation. So if you don't, if some notation is unfamiliar to you, you just ask. Okay, so none of this is very complicated. Yeah.
This squiggly arrow meaning like there's like some f of v1 that goes like this, which is y1.
Yeah. So no, we are given both v1 and y1. So we are given pairs like vi, yi, where v is a vector and this is and yi is some value. And ideally, you would like to have some f of vi equals yi, like you're saying. But the goal in linear regression is to say, oh, okay, what if this f is only supposed to be a linear function? Yeah, so f of vi is supposed to just be inner product of vi with x. Okay, and you try to find the best such x so that f of vi will be approximately equal to y. So here the arrow just means that corresponding to vi you have this value y. Right? So this is so as you can imagine, this is very common in various learning type applications, like maybe you have some classification or something like that, some classification task, and you may want, and you have some observations and you have some value associated with that observation, and you want some linear function that best fits these values. Okay? So this is something that many of you have seen. And why is this optimization? Right? So this optimization because this is now the function that you would like to minimize. Okay, and this is a well-defined objective function, and it's an unconstrained optimization problem because I don't have any constraints on my variables x. Okay. So the variables here are x, I going from 1 to n. No constraints, and objective is minimize so this is the goal of regression. So we can abstractly phrase it as just that. So this is one classic example that some of you will have seen. Otherwise, you will see slight variants of this in the homework. Okay, so this is regression. So, and another classic example again is linear optimization, and here it's constraint. We'll see more of this later in today's lecture and also next lecture. Okay, so what is linear optimization? Here you have variables. Okay, you have variables x1, x2, up to xn, and these are, let's say, real values. So that means each xi is supposed to be a real number. And now we say that it's linear optimization because now everything is linear. Okay, like the objective is now a linear function. Objective is to, let's say, maximize. You could also say minimize, doesn't matter. So maximize some c1 x1, c2 x2, ci or something. So the variables are real valued. Objective is some linear function of these variables, and constraints are also all linear. Are all of the kind some a11 x1 b1 and so on. So you have a bunch of linear constraints and linear objective. So this is why it's called linear programming or linear optimization. So this is another canonical example of optimization, and turns out this can actually be solved efficiently if the number of constraints in time, which is like polynomial in the number of constraints, number of variables, so on. Okay. So again, we will come back to that. So any questions on this notation? So this is again the simplest kind of setting you can imagine. This is just linear constraints, real value variables. Yeah.
Are the constraints kind of like hyperplanes and are?
Oh yes, we'll come to that. Yes. So for linear programs, there is a very clean geometric interpretation. So each constraint can be thought of as, if you think of the n-dimensional real space. Okay, so that's like each xi is some coordinate direction. Okay, so that's the n-dimensional real space. I'll just write it as x1, x2, let's say x3, and so on. Then each constraint geometrically turns out to be some kind of a half space. Okay, so it's like should have drawn 2 dimensions, but it will just be something that looks like this. And a constraint will all the x's that satisfy this constraint will be things that are on one side of this plane. So in 3-dimensional space, you'll have some plane, and one side will be x's that satisfy this constraint, the other side will be x's that do not satisfy this constraint. So if you've got to satisfy all of these constraints, then it means that you are looking at an intersection of these half spaces. So the set of feasible things of one such constraint is called a half space, because there is this plane that is dividing space into 2 regions. One region is satisfiable, the other region is not. So the satisfiable part is like a half space. Then you have a bunch of these guys, so it's an intersection of half spaces, because you want all of them to be satisfied. So yeah, for linear optimization, there's a very clean geometric view of what's going on. Alright, so that's linear optimization. Okay, so our goal will actually be to write discrete problems as optimization. Okay, and we'll see how this can be an interesting thing to do. Okay. So I put up here a few things that you've seen before. There are, some of these things you've seen a while ago, so I will redefine those problems. Okay. But the general goal will be to say, okay, so there are, so these are like the canonical applications of optimization where you have some continuous problems. But it's also interesting to think of optimization formulations of discrete problems, which, and that will be our goal. So what you'll see is that to express discrete or combinatorial and try to get some new algorithms for these problems using optimization as a platform. So that will be the goal. And this is often something that you will realize, like in many problems, you can actually come up with some optimization formulations. And you can try to solve these things and hope for the best, right? So that's a very common thing to do in practice. That's the reason I end up doing optimization in this course. Alright, so let's start with some basic examples. So these examples, some of them you realize are easy to express as optimization and some not so much. Okay, so that's why I have like 4 examples of this. So let's start with the simplest example, which is matching. Okay, so this is the matching problem. This is a slide from maybe 10 lectures ago, so I just recapped. Okay, so you have a bunch of children and a bunch of gifts, and each child has some happiness value for each gift. Okay, this we said was Vij. You'd like to find an allocation so that the total happiness is maximized. And the total happiness is just defined as the sum of the happiness values of this assignment. So this is one problem that we solved. And this is also called bipartite function. Okay, so we had this bipartite graph. U is the set of children. Okay, or maybe we call it A and B. A and B. B is a set of gifts, A is a set of children. You'd like to find an assignment. So that the sum of these happiness values is maximum. So now my question is, how would you try to phrase this? Suppose you were to try to phrase this problem as an optimization. So how would we go about doing this? Right? So remember that the problem naturally has some kind of constraints, right? So in the sense that, every child has to get exactly one gift, and and you have a natural objective, which is that this total happiness value has to be maximized. So in some sense, you can see some constraints and you can see some objective, but how do you formally kind of phrase this? Right? So that's what we'll see now. But any problems recapping the problem itself? Questions? All right. Okay, so if you want to write such a problem as optimization problem, actually in general, if you want to write anything as optimization, you've got to be asking yourself 3 questions, right? One is, what are the variables, what is the constraints, and what's the objective? And very simple things. So, what are nice candidates for variables here? What would be a good way to capture this problem? Yeah?
So it might be happiness with such children, maybe?
Sorry?
gifts and children.
Okay.
Yes.
So those are given, right? So Vij values are given.
Yeah.
So no point having them as variables because you know their values, right? Like Vij's are all given. Yeah. So, but you're right. I mean, in some sense, what you're trying to say is that you would like to know which child was assigned which gift, right? That's something that these variables should be able to capture. Yeah.
We have a permutation of the numbers 1 to n that represents the assignment of gifts.
So that's the solution, right? So what you're saying is that what you want is a permutation, okay? But what should, I mean, if you were to try to write it as an optimization problem, what should actually the variables of this be? Actually, yeah, continuing along those lines, you can.
So you could have a discrete variable of like whether child 1 got gift 1 or whether child 1 got gift 2, and then you could write constraints of like you have to have less than or equal to 1 for each sum of gifts because each gift goes to 1 child.
Okay, so that's one way of formalizing what you just said, right? So I think what you said is maybe your variable can be things like what gift is child I assigned, okay, and then you would have a discrete set. So that's one formulation. The other formulation, which which we'll see is a bit more clean, is just have binary variables, okay, where you say that, oh, okay, did child I get gift J? Okay. So let's write out both of these things. So you can have two choices. And is yi is index okay. And you would like all these yi's to be distinct. Those would be the kind of constraints you would write over there. Okay, but you will realize that if you write those kind of constraints, writing down the objective becomes a bit more tricky. So, but yeah, so let's not go too much into that. Okay, so the other candidate that she mentioned is have Boolean variables. Which is have variables which are of the kind xij supposed to denote child So if child I receives gift j, this is supposed to be 1, and otherwise this is supposed to be 0. Okay. So note that I'm using the word supposed to be. So when we define our variables, we have in some sense the intended solution, right? So we are thinking of how these variables capture our intended solution. Our intended solution is a permutation. Right? It's like every child needs to be assigned 1 here. So we define these variables and we say that, oh, okay, this is supposed to be 0 if it's this and 1 if it's this. Okay. All right. And now, and you can now think of constraints. So I will go with candidate 2 because I think candidate 1 will be a bit tricky to write constraints for. You'll have to say that when I is not equal to j, yi is not equal to yj, something like this. And then the objective becomes a bit more tricky to write. Okay. So let's go with candidate 2 for now. So here the constraints, like what I mentioned, are exactly that for every I, every child must get exactly 1 gift. Right? So that's what we know about this. So So we have sum over j xij equal to 1. So this is one constraint that any feasible solution must satisfy. Like yeah, if it's equal to 0, then it's like saying that child I does not get any gift. And if it's 2, let's say, then it means the child I is getting 2 gifts, which is not what. That's good. Now, so this is one constraint if you want. And of course, you can also view these things as constraints. So each xij belongs to this discrete set 0, 1. So that's one thing you can add. You may also think that, okay, every gift must go to exactly one child, right? So that's a valid constraint. But if you think about it, you maybe don't have to explicitly write it, right? Because if every child receives exactly one gift and you have exactly n gifts and n children, then it has to be that every gift goes to exactly one child. So is that clear? Okay, so but if you want, you can write it. So let's be fair and say for every. Okay, is also equal. Okay. So these are all valid constraints that you can put on these variables exactly. Okay. And now, what is the objective?
Shouldn't we define the weight for each xij?
Right, so that's given to you, right? Like the you mean the v value?
Yes.
Yeah, so the v value is given to you. Right, that's a good point. So what he's observing is that so far we have not seen any v's in the current thing. But where does it show up?
The objective.
Yeah, so it shows up naturally in the objective, right? So now your objective can be is supposed to capture this total happiness value of this allocation. Okay. So the objective, if you think about it, what is the objective value? It's like supposed to be the total happiness value of our assignment. Okay. So how do you write it in terms of our xij variables? Anybody else? Okay.
The xij variables form a matrix, and then is the product of that matrix and the weight vector, like the happiness vector.
Okay. So if you think of, so what he's saying is, okay, let's look at this matrix x1, 2, xn1, xn2. So these are some binary variables, and put them in a matrix. But the happiness is also a matrix, right? Because we have Vij, which is the happiness value of the child I gets when he's assigned J. So you sometimes have two matrices around. You have to do something that combines these two. So that's right. But, yeah.
And then
Yeah.
summation of all those things.
Right. So what he's saying is you can just look at sum over all ij, and then you can look at vij times xij. And this is our objective value. Okay, so why is this, right? So ideally what we would like to do is sum over children I of v I j, where j is the gift assigned to child. So this is what we would like to do, right? So sum over children I of v, the value of I and the gift that is assigned to I. Okay? But note that this is exactly the same as that quantity, because if j is the right gift assigned to I, then the corresponding term in this summation would be vij. For every other gift, the xij value would be 0. Okay, so this value is exactly the same as this. Okay? So let me not write j here. So let me write gift of I. So ideally, we would like to have given to child. Okay. So this is what we would like to write, but this is exactly the same as that, because from the way we set up our constraints and equation and these binary variables, you have xij equals 0 for everything that is not assigned to I, for all j that is not assigned to I, and if it's equal, and for the j that is assigned to I, you have xij equals 1. So you get, so these two quantities are exactly the same. So is this clear for everyone? This is very simple, but you have to know that there is something, yeah, so coming up with that takes a little bit of thinking. Yeah.
So theoretical aspect of
Yeah.
and you were saying that the second constraint, the second line for every bj sigma
Yeah.
is optional.
For this formulation, yes, because if you have n gifts and n children, and you are guaranteed that for every child gets exactly one gift, and these xij are all in 0, 1.
But you can assign a gift more than one child. So you need to mention the second.
Right, but if there are n children and n gifts, okay, and you ensure that every child gets exactly one gift, okay, now how could it be that two gifts go to the same child, right?
For example, if we consider a 2 by 2 matrix, so just put 1 in the first column. Okay, so you know the first gift is assigned to first children and the second children.
Okay, so what is the matrix that you're trying to construct? So you have 1.
And the first column are 1.
Oh, both 1.
Yeah, those 1.
Okay,
1, and the other ones are 0.
both 0.
Both 0. 0, 0. Okay. and this is value mainly for the first constraint, yes? But it's not a value defined. You need to the second constraint to it.
Ah, okay. Yeah, you're right. Okay, so I missed this fact. Okay, so so he's totally right. So what he's saying is, if you did not have this constraint, what you would have is, you could just have like one guy assigned to everyone, and these things not assigned to anybody else, and this would satisfy the condition that you, right? So this would satisfy both all xij being 0, 1, and it would also satisfy this constraint that for every child there is exactly one gift that it gets. Right? Yeah, sorry, I should have realized. Okay, yeah. Okay, so do you all see this? Do you all see this issue? Actually, it's a very nice introduction to what I was going to say next, which is that the way you define constraints should be such that if you didn't have any context about the problem and you just have these constraints, then it should be telling you everything you need to know about the problem. Okay. And that is very important when you come up with an optimization formulation. Because the goal is you will now take these constraints and you will feed it to some optimization solver which knows nothing about the problem where it came from. Right? Like your optimization solver may not know that, oh, okay, you are trying to capture this problem with like children and gifts and so on. It just knows that, oh, okay, I just want to optimize with these variables and subject to some constraints. Okay? So, and that's why this kind of sanity check is very important. So good. So we need both these constraints, and otherwise you have issues like that. Okay. So any questions on this example?
So the problem here was you said that one was optional, when it really isn't optional.
Yeah.
You have to have both.
Exactly.
constraints.
You've got to have both constraints to make these things. Okay. And in fact, so I was going to skip that step, but it's often you need to convince yourself that this optimization formulation is actually the true optimization. Actually captures the problem. And that argument would have revealed the issue that he was saying. Yeah.
So now we have our variables, we have our constraints, we have our objective. Now is our goal just to map it to one of our optimization functions that we previously saw, or how do we get from this to our optimizer black box?
Right. So now what do we have? Right. So what have we done? We have defined these variables xij, which are supposed to be binary, and we have these constraints. Right. So you have n constraints for children, n constraints for gifts, and we have these guys. You can view them as constraints. Okay. And you feed them to this black box optimization solver. Okay. And what you will say is that you try to maximize this quantity subject to all of those constraints. Okay. And the black box does its thing. We don't really care for now what it does, and it produces some values of xij. So it's worthwhile maybe writing this explicitly. Okay. So we take our formulation. So this is like let's call it the optimization paradigm. Okay, so we have some problem. In this case, it is matching. And is you convert it into a K constraints are these like these 2n constraints that we wrote down, and also Xij belongs to 0. And the objective is maximize okay. This is your optimization problem. And you feed this optimization problem into this oracle. And this oracle is supposed to take any optimization problem and produce the best solution. Okay. So this oracle will give you specific assignments. So this oracle will give us some values for Xij. Okay. And from this, you will need to convert to a solution to the original one. Okay. So this is the general paradigm that we will be using. Okay. So that's how everything fits. So is this picture clear? So we take our problem, convert it into some optimization thing, and the oracle, like I was saying before, knows nothing about the original problem. It only sees these constraints and some variables, and it produces the best possible solution for this phrasing. And your constraints and objective and everything should be such that from these values of Xij that you have, you should be able to come up with hopefully the optimal solution to the original problem. Okay. And what we often, so when we try to cast a problem as optimization, we have to make sure that this procedure is all valid. Okay, which is to say that, and the key step that you have to verify is valid is that suppose you have an optimizer that solves this thing, and can you actually convert it into a valid solution for your original problem? Right? And if you are able to do that, then your formulation is correct. So if I had, for instance, started with the incorrect formulation that I had written originally, okay, without the constraints that every child has to do it, then you can go until this step, and the oracle will produce something like this. Okay? But you will have trouble converting that into a feasible solution for the original problem. So that was where, for instance, that's where you will realize that it's important to have the right optimization problem. So let me pause here for a bit, because I think this is like the most important part of maybe slide of the lecture. Questions, comments?
So like we made our black box opt problem, whatever.
Mm-hmm.
So we have to prove it's correct now.
Right. So what does it mean to prove that it's correct? It means that you can actually recover the solution to the original problem using a solution to that. Right? Yes. In general, so that's what you need to do to prove that it's actually a valid formulation for your original problem. But I won't stress it too much, because usually it is somehow it's somewhat easy, right? And yeah, but sometimes you run into problems like I. In fact, I will only give examples of the kind where certain formulations don't exactly capture, but in general you have to complete.
You recommend we have 2n constraints, but we also have the constraints that Xij.
Right. So it's whether you treat it as a constraint or something about the variables. If you really want, you can throw those also as constraints.
But having like polynomials that are constraints
Is always fine. Yeah. So we assume that having some kind of polynomial bound. In fact, I mean, in general, these kind of binary things are difficult to solve in general, but usually you can relax those to some linear constraints and then you can solve. Yeah, so that we will see next couple of days. Okay, and let me also write out what he's saying, which is that formally showing that is usually rests on this step. Converting a solution that the oracle gives you into a solution for the actual problem, and showing that this can always be done. That usually requires some proof. All right. So let's see a second example. If there are no more questions about this. All right. So this is another example which we saw last time, which is the set cover problem. Okay. So this is maybe we saw it when we were looking at greedy algorithms. If you remember, this was our first example of an approximation algorithm. So the problem was you have n people and m desired skills, and each person has some subset of these skills. We do that as an edge in this bipartite graph. So person 1 has skills 1, 2, and 5, I guess, okay, and so on. And your goal is to pick the smallest number of people so that every skill is covered. So this was the set cover problem. And yeah, so now let's try to capture this as optimization, as some optimization problem. I feel this is actually a bit easier even than the previous example. And like I said before, you should always be asking yourself these 3 questions, right? Like what should the variables be? What are the constraints and what's the objective?
Variables are the connections between n and m, obviously. This is going to be similar to the child gift problem.
Well, if you think about it, that's not sure. Okay, so let's say your variables correspond to these edges. Okay. Now, should they be, what kind of variables should they be? Let's say they are binary also. Okay?
Yeah,
so let's say they are binary variables.
I would say a matrix n by m.
Okay.
Similar to what we did with the gift problem.
Okay, so one suggestion is, yeah, let's say you have xij variables. These are supposed to be 0 or 1. Okay, fine. But what is your intuitive representation of, so what should they mean? So is it supposed to be 1 if what?
1 if there's a connection. So
Okay.
x11 would be set to 1, but x13 would be set to 0.
Sure. So now what you're defining is, this is just the adjacency matrix, right? So why are they variables? Their values are already known to you.
Okay.
Right? Because remember, you're writing your formulation after you're given your instance, right? Which is like after you're given this, the instance of this problem. You're not writing your formulation before you actually know what this graph is, right? So you're actually given the graph. And for this graph, you write this optimization. Yeah. Okay. So what she's suggesting is you have variables xi corresponding to each person. Okay. And so this is person I, and xi is again supposed to be 0 or 1, and it's 1 if the person I is picked in this set and 0 otherwise. Okay. Remember, variables are always supposed to encapsulate the desired solution, right? Because that's our goal, right? Like, oh, sorry. Okay, so this thing crashed. Okay, yeah. In the past, I've had experiences where the notes would disappear and then I have to rewrite them from scratch. So, luckily, that did not happen. So, okay, so in our previous slide, we have this thing that somehow your values for xij should allow you to recover a solution to the original problem. So that's something you've always got to have in mind when you're writing a optimization formula. So if it's something like this, it's clean because xij being 0 or 1 exactly captures what you want. Right? You're supposed to pick a subset of your people, and if xi is there, you pick the person, otherwise. So that's good. And now, okay, so variables are xi for each person I, and supposed to be 1. If I is chosen as set, and 0. Okay. So what are the constraints? So again, the problem statement here makes it somewhat easy. So what should the constraints be in this case? Yeah.
You make one constraint for each skill, and you have all the people that have that skill. So that's equal 1 for each one.
Yeah. So what you can do is you can look at each skill. The constraint is basically specified in the problem statement, right? It says that every skill is covered. That means there's at least one person chosen who has that skill. So you look at a constraint, you look at all the people that have that constraint. So for each skill j, denoting by Sj set of people. So now you can write sum over I in Sj of xi. Okay, so sum over all people in this set Sj, okay, to be defined as the set of people who possess skill j. So that must be at least 1. Okay, so you must have at least one person who has that skill. Right. This is again. So you have n constraints here. Maybe it was m. Yeah. So we have m. One for each skill. Right. Okay, and now what is the objective value? Your objective is, again, it's specified in the problem, right? So pick the smallest subset of people. Yeah.
So the sum of xi is minimized.
Yeah, so your goal is to now, so the objective is now very simple. Just to minimize x1 plus x2. So we have NP. So you just want to minimize sum over all I of x. Okay. So this is I think a very simple formulation. Right? So it's just the problem. So some problems are like this, where somehow the problem definition itself naturally lends itself to an optimization formulation. And here, like you were saying, formally proving that, like if you have a solution to this optimization problem, you can actually convert it into a solution to the original problem is actually rather trivial, because somehow these variables naturally tell you if you should how to do this conversion. Okay. So for some problems it may be tricky to do that, as we'll see later. But yeah, for most basic problems it's actually very straightforward to go from the formulation to an actual. Yeah?
So where did you capture this feature? For example, the person 1 has a 1, 3, and 5, and not 2 or 4.
Yeah, you tell me. So his question is, how is the structure of the instance being captured, right? Like we saw that person 1 has these skills, and person 2 has some other skills, and so on. How exactly is this information coming into the formulation?
Maybe it doesn't matter, right? Because when we are writing these constraints.
Exactly. So it comes up in this constraint, right? So saying what all skills person I has, that information is exactly the same as giving information of who are all the people who possess skill J. If you have this for every J, then it also tells you corresponding information about it. So that's how the information is captured. Yeah.
So for these two problems, when we were looking at them, we spent a fair bit of time trying to figure out how complex our solution would be and how long it would take. So with an optimizer, I mean, when we frame it as an optimization problem, we just kind of aren't even looking at that, right?
Yeah. So I mean, we ultimately have to, because you have to solve this. So his question is, when we originally studied these problems, I think that's what you meant, right? When we originally studied this problem, we started. We were thinking of, is the running time for this like n cubed, n to the 4, something like this. Right now, we are not talking about that, right? We are just talking about writing this as an optimization formulation, sending it off to an optimizer, and hoping for the best. So ultimately, we have to think about how long is the optimizer going to take, how many constraints you have, and so on. In fact, my next example is going to be one where the number of constraints I have will be exponential. So in such cases, there's not much point trying to use an optimizer, because even a typical optimizer might take too much time. So there you'll have to come up with other tricks. So, but for these problems, it was pretty clear what you're doing, right? So you had 2n constraints, and at least also, like you were mentioning, maybe if you include the variables, then you have n squared plus 2n constraints, and you had an optimization. And here it was just like n variables roughly n constraints. Alright, so let's see a third example. Okay, so this is, so the goal of today is to make you somehow think of how you come up with optimization formulations, right? So we'll see a bunch of examples. So this is, I think, a non-trivial one. Okay, so here, this was spanning tree, where you have some simple undirected graph and edge weights some WE. You want to pick a subset of the edges so that all the vertices are connected to one another. just using the subset of edges that you've picked, and the total weight of the edges that you've chosen is as small as possible. Right? So this is a problem for which this simple greedy Prim's algorithm gave something like O of m plus n times log n. But this will actually be a case where his point is illustrated but in reverse. Okay, so where the simple algorithm the greedy algorithm is super fast, but writing an optimization formulation will lead to a huge formulation, okay, like an exponential size formulation. So in a problem like this, writing down the formulation and trying to solve it using this may actually be a waste of time. Okay, you would rather come up with a much nicer solution like Prim's algorithm. You seem unconvinced.
No, I'm not unconvinced.
Okay.
It's just, yeah.
Okay.
I mean, the variables should be simple. It's just just 1, 0 for each edge.
Yeah.
That you select.
So you at least So now you are getting a good hang of how to pick the variables, right? So the variables should tell you what your solution should be. Okay. So and you have to pick a subset of the edges. So your variables are clean. So variables are just xe for every edge. 1 for every edge. And these are supposed to be binary. And your objective is also very clean, right? You want the total sum of the edges that you picked to be as small as possible. So, and now we can use exactly what we did last time. So you can say that, so formally, like saying sum over all E such that xe equals 1 of W, which is the same as sum over all x. So this is exactly what we saw in this matching type problem, right? So it's the same trick. What you want is the sum of all the edges you picked, and because these are binary variables, you can write it also as sum over all edges of WEX. Note that if you had something like this, you can't feed it into the optimizer because the optimizer finds the solution. It does not know this. Right? It cannot interpret this constraint. Okay, so that's the reason we write it like this. Okay. All right. So these two are easy. So now, what are the constraints? Right. So the constraints are supposed to say that all vertices are connected to one another. And the question is, how would you write this as constraints involving the variables that you pick? Yeah.
So at least the number of edges should be greater than or equal number of vertices minus 1.
Okay. So what he's saying is this is a good start. Okay. So what you want is so you have some graph, let's say, and you have xe for every edge. So what he's saying is that if all the vertices have to be connected to one another using only the edges you've picked, you have to pick at least n minus 1 edges, where n is the number of vertices in the graph. Because you should at least be a tree, and you know that a tree has exactly n minus 1. Okay. So we know one constraint is that sum over all E x is fact, given that your solution will be a tree, you can even say it will be equal to n minus 1. But let's not worry about that. Yeah.
The most confusing thing for me about writing all of this is the constraints.
Yes, and it should be that way.
Okay.
Yeah.
Well, I just want to know if there's limitations to what kind of constraints we can give the program, right?
Right.
For example, if we do something like this, can we just say it has to be equal to n minus 1, and it will accept that?
Right. Okay, so let me. So what he is asking is a more general question, which is so far all my constraints just happen to be linear, and I guess what you're asking is, should it always be that way, or am I allowed to use, let's say, quadratic constraints? Okay. In general, optimizers take reasonable constraints. For instance, you can give quadratic constraints also in principle. But it's just that the complexity of the solvers we know just grows very badly with the complexity of these constraints. Linear constraints are usually fairly easy to optimize with. So you would hope for constraints that are as simple as possible. Yeah, but as such, for now, you can think that there are no restrictions. Yeah.
But there's also, like, in the first one we had where xij is either 1 or 0.
Mm-hmm.
So there it seemed like an option of several different linear constraints. Where it's like it's either 1 or it is 0.
But why? What do you mean? I don't understand.
Well, I feel like that's not a linear constraint if it's 1 or 0.
Oh, right. Yeah. So I agree. So that's why I'm slightly making a distinction between the domain of the variables, which is like, oh, the variables are binary and they should be 0, 1, versus constraints of this kind, which are like some inequalities. Okay. Yeah. That's a perfect point. Yeah. That's why I've been making this slight distinction of. That's why when he asked this question of, oh, isn't that a constraint? I said you could treat it as a constraint, but let's not do that. Right? So, and that's exactly the reason. Right? So there is this slight difference between what is the domain of the variable and what is constraint. So you can encapsulate constraints like that if you are allowed things like this. If you are allowed xe squared equals xe, this would mean that xe is either 0 or 1. Okay, so you can, if you are allowed some quadratic stuff like this, you can play tricks like that and encode it as a constraint. Okay, but that's why I called it a domain constraint. It's like, okay, you optimize over this domain, which most optimizers will allow you to do. So, yeah, so that's a little bit of an aside. Alright, so this is one constraint that is certainly necessary, okay, so to ensure that everyone is connected to everybody else. And as you will easily observe, this is not sufficient, right? Because in this example, I have 6 vertices, 7 vertices, sorry. And I can choose all of these edges, and I have chosen 6 edges, 4 from the cycle and 2 outside. So I have satisfied this constraint, but of course I have not connected the last one to everything. So now he will come up with an easy correction which says for every vertex there should be 1 edge out of it, right? Or no, something like that, right? So actually that was depicting right of the graph. Okay, yeah. So another thing you could mention is to say that so in a cycle you should not be selecting all the edges of that cycle, right? Because your goal is to only pick a graph that says cycle. Okay, so that turns out to work, but we'll get to that in a bit. Okay, so another constraint that you can write, I thought this was going to come up first, is that at least in this example, the reason that things were bad is because this was the only edge out of this vertex 1. If you don't pick it, there's no way you can connect it to the rest of the graph. So you might think that for every I, sum over edges adjacent to I, edges E together. So this is again a constraint that any spanning tree should satisfy. Because if you hope to connect this vertex to every other vertex, and your graph is not like a single vertex or something, you must have one edge going out of every vertex. But again, there are examples where these two will not be enough. Okay, so you can come up with some examples where, yeah.
If we set the first one to strictly equal,
Yeah.
I feel like it should be enough.
So that along with this,
Yeah.
you mean that one along with this?
Yeah.
Yeah, so that will be a good exercise, right? So to come up with examples where somehow, even if you had that one exactly equal, and you had this kind of a constraint as well, turns out this is not quite enough. Okay, so you need more constraint. And one set of constraints that he mentioned is saying that in every cycle, so every the idea is to have a constraint for each cycle. Okay, so let E1, E2 up to ER be the edges of some cycle. Then some XE1 plus XE2 R is less than or equal to R. So this is one way of eliminating that solution, right? But if you, but what I would like, maybe it's not that important to follow the details, but what you should understand is the process I'm doing, right? I'm trying to write some constraints, okay? And I'm asking, are they enough, right? And what does it mean, are they enough, right? So in some sense, I'm trying to answer the exact kind of question that he pointed out with my original constraints, right? For the magic wand error. I'm just saying, oh, suppose there was an optimizer that saw these constraints and came up with a feasible solution to that. Will I now be able to recover a feasible solution to the original problem? Okay, and that is what was not satisfied when you had something like that, right? Because I came up with some solution which satisfied that constraint, but somehow it did not translate to a solution to my original problem. So that's something you've got to pay attention. Yeah.
So why wouldn't it work just to say that you have at least one edge out of everyone and have an objective function that minimizes the number of edges?
Yeah, so you mean a constraint like that, right? Also have a constraint that says sum over all edges xc equals n minus 1. Your objective was this weighted thing. So your objective was the original problem had weights. So the objective we have already fixed. But you could say that, yeah, you could still have this as a constraint. And this is what here also asked. Like if you have that constraint and these constraints, wouldn't it be enough to force a tree? Right? Or force at least something like a tree.
Why do you even need the other one? Isn't it just enough to say that you need an edge out of every vertex?
Right, so let me try to come up with a counterexample for this. Okay, so okay, so how many
Connected triangles.
Yeah, so 3, 4, 5, 7. Sorry. Oh. Yeah, I'm just making sure I get the number of edges right? So, so I have 1, 2, 3, 4, 5, 6, 7. Okay. I don't even need this. Okay, so now I have 6 edges. Okay, so I've satisfied that, and I have an edge from every vertex. Okay, but this is not a tree, right? Because there is still a problem. Yeah.
So back in the homework, we had this like A to the K matrix, and if we make K large enough, we can actually look at it and make sure there's some kind of path. Seems like we can use that to make sure everything's connected.
Right. So this is actually a very interesting solution, and it turns out this works. Okay, but it will lead to. So what is the general idea? If I understand what he's saying correctly, is to say that if you had variables for every edge, and you're allowed to take products of those variables. Okay. So if you do it the way you are suggesting, it will turn out to be like basically products between these xe variables. Okay? And if you are allowed to take products of this x matrix with one another, then it turns out you can actually represent this, right? Because one way of saying that the graph is all connected is to say that from every I there's a path to every other j. So you could say that if I take this x matrix, which basically is like, which tells you which edges you have picked, and then I take x to the power of essentially n, then everything would be bigger than, all the entries have to be bigger than or equal to 0. So you could actually say that, and these are valid constraints. It's just that these now become polynomial constraints because you now have products of these xi's showing up. Okay? Yeah, but that's a very good solution. In fact, yeah, last year I had a small note. Maybe I will post that up, which explains exactly the solution of it. Yeah. In fact, people often come up with that solution as a way of writing shortest path as an optimum. Okay. So that's where this kind of thing comes up. But you know, here again, you could do that. Okay, so this thing turns out as valid. But next class we'll see a slightly different solution, which is basically inspired by this counterexample. Okay, but both of these have exponential size because there are exponentially many cycles. Okay, so let's continue this next. Oh,